Good afternoon, everybody, and welcome to the Parsons Technical Webinar Series. I will be your host today, Jessica Bennett. We are honored to have with us today Dr. Jeffrey Evans, presenting on soil-bentonite slurry walls, what we've learned from the last 50 years of practice and research. So a few housekeeping items up front. We will be keeping everybody's lines muted until the Q&A session at the end. If you have a question at any time during the presentation, you can either enter it into the Q&A feature, or you can hold it until the end and raise your hand and ask it live. This webinar has been approved for one professional development hour credit or PDH credit. If you would like to receive a certificate for that, there will be a link in the attendance, a link to the attendance form that's posted already in the Q&A section. There's 3 multiple choice questions you'll need to answer, so please take a look at those. And if you have any issues getting that form, let us know. And if you miss any questions, this webinar is being recorded and will be posted to our YouTube channel in the next week or so. So just a brief agenda for today. We'll introduce our guest speaker, followed by a core value moment before we get into the technical presentation itself, and then we will wrap up at the end with a Q&A. So a little bit about our presenter today. We have Dr. Jeffrey Evans with us. He's one of the world's leading experts on slurry walls and barrier wall technologies. He has worked for the U.S. Army Corps of Engineers and has been a consultant for slurry walls in 15 states and 2 Canadian provinces, and has authored over 70 different slurry wall related papers, as well as several books. And he's also a professor emeritus at Bucknell University. And with that, I will hand it off to Jeff for the core value moment.
All right, very good. Thank you for the introduction. Thank you all for joining. I come to you from sunny San Luis Obispo, California. So I hope your day is as nice as mine. So we'll start with the core value. These are currently the 5 core values of Parsons, and I've chosen innovation to tie into slurry trench cutoff walls. And some synonyms for innovation: improvement, advancement, originality, invention. The core value says, through inventive processes and unique solutions, we provide unmatched value to our customers. So we're only innovative if the solution for any new project is informed by lessons learned on previous projects and the latest developments in the field. The other aspect of being innovative is to recognize what we actually know and what we're assuming we know in the system. So one of the things I've sort of valued throughout my career is do not hesitate to question. That's how we learn. That's how we become more innovative. If someone tells you it's this way, well, maybe it is, maybe it isn't. That's how we progress. So with that, the topic being slurry trench cutoff walls and 50 years of what have we learned. First, I'll do an overview of how we use these vertical cutoff walls or slurry walls, what the historical context is of them, so we're all on the same page there. Then we'll talk about how they're built. This may be old news for some of you, new news for others, and what we learned in that regard about how the backfill moves beneath the slurry. So this presentation is different than one I gave a couple of years back, where it was an overview of a whole variety of techniques. Where here we're going to dig more deeply into the most commonly used technique in the U.S., that is soil-bentonite slurry trench cutoff walls. And we've learned a lot about their properties, about how they consolidate, how that influences the state of stress, how the state of stress influences the hydraulic conductivity, which usually is the key parameter for us, how they hold up in the environment in response to, cycling wet and dry, how durable they are, how they hold up in an environmental contaminated site environment in terms of compatibility, how even with low hydraulic conductivity, we still have diffusion. And then the concept of membrane behavior, and I don't mean HDPE, I mean the concept of cation exclusion, membrane behavior. I'll tie all these new things that we've learned over the years into how that informs our current design approaches, and then I'll provide a summary of where we stand. So let's start with primary functions, and this is a topic today about soil bentonite slurry trench cutoff walls, but the functions really can be done with other types of cutoff walls, in situ mixed walls, self-hardening slurry walls, but we're going to, so these functions are more broad than just soil bentonite. So first is dewatering. We started using these and we sort of proved the technique out by using them to assist in deep excavations below the water table to reduce pumpage and increase stability. Um, and then we used them also in the early days for cutoffs for dams and levees to reduce seepage, improve downstream stability. Um, the big push came when Superfund passed and we had environmental containment to reduce seepage quantity into or out of contaminated areas, to help pump and treat systems work better, and also to build the funnel and gate treatment systems that we sometimes will apply to contaminated sites. More recently, and these involve the addition of cement, we use them for shear walls, for downslope stability, for landfill stability, for liquefaction mitigation. And finally, developing along a parallel line of slurry walls are what are more correctly or more precisely called diaphragm walls. And these are structural slurry walls where the backfill is reinforced concrete, which is very different than the backfill we would use for an environmental site. So let's look at some pictures of these functions. So I like this picture, even though it's way out of date. It's my first slurry wall project. I learned about slurry walls in the early 70s at Purdue, and I got a chance to apply this for a deep excavation for a pump station. So you can see the slurry wall being cut along the screen here, along the side, but you also see to the right a channel. You see in the distance Lake Michigan with all kinds of cranes floating on it. And basically what we have is dune sand, and we want to excavate 50 feet below the water table to build a deep water discharge pump house. And this slurry wall was put around it, and we dewatered the bathtub that we had created. And once we did that, the excavation was maintained, and the only time we ran sump pumps is when it rained. So this was a full-scale test of slurry trench cutoff walls, and really convinced me that soil bentonite can do an amazing job at cutting off the flow if properly built and designed. So that's dewatering. We use them for cutoff walls. This is a cross-section of the Herbert Hoover Dike where the dike had undergone significant downstream leakage and what really wasn't a properly engineered and built dike. And so to build a cutoff wall through the dike to cut off seepage through the dike and beneath the dike was the chosen technique to stabilize the dike against failure. So that's dams and levees. As I said, with the passage of Superfund in the 80s, these really took off. This was my first environmental project. This is a landfill in Baltimore, Maryland. You can see the landfill to the right. You can see the slurry wall in the upper left of the picture. You can see some backfill being made above the text. And you can see a road running longitudinally right along the top of the cutoff wall. Garbage trucks ran. It's a closed landfill now. They monitored for a dozen years, and then in 1980, the EPA declared no further action needed. And every year they monitor it and they put out a report that says this cutoff wall in connection with an inboard leachate collection system is protecting the environment, the Chesapeake Bay. So long history of using these for environmental containment. They're not always circumferential, which is shown on the left of this slide. Sometimes we use them up gradient so that clean groundwater doesn't become contaminated. And then we pump from the downstream side and we can capture the plume. Sometimes we use them on the down gradient side if we want to use groundwater to help clean up, if you will, to flush the contaminants from the soil. This is the layout that was done at Rocky Mountain Arsenal. All these show a key into the subsurface environment. Um, they don't have to key, they can hang, and the Herbert Hoover dike was an example of that. We do use them, slurry walls, for shear walls, and the top picture is the Manhattan, Kansas Tuttle Creek Dam. And liquefaction analysis showed that if an earthquake came along, this soil would liquefy, the dam would fail, and it'd be like 800,000 people drowned in Manhattan, Kansas. So to stabilize this against liquefaction, there were cutoff walls put perpendicular to the dam. Now these were done having concrete in them or cement in them, and this was actually a self-hardening slurry wall compared to an SB. And here's a landfill to the left, and shear walls. And this was actually done by in situ mixing. And I throw this slide in just to say the focus of this is a deeper dive into SB, the most commonly used technique. But there are other techniques available of both slurry walls and in situ mixing techniques that may actually be more applicable to your project. And then the last of the applications, as I mentioned, are structural slurry walls. This is in the inner harbor area of Baltimore. And you can see a slurry trench, and this is called a hydrophrase. It's excavating soil in panels, but instead of having some particularly low permeability, it's an incredibly high strength material. So a cage is prepared in the surface, the cage is lowered down, and then concrete is placed by Tremie. So the slurry wall becomes a structural concrete wall, and sometimes it needs bracing, sometimes it's cantilevered, it can be internally braced, it can have tiebacks. These are cutouts for tiebacks. But this is a common structural technique and the subject of a whole nother lecture. But you can actually see sometimes these come out so nice, they leave them as the wall. They don't put a finish. So there's an underground station in London where you can see the slurry wall. There's some parking garages at MIT and Cambridge where you can see the slurry wall. Very commonly used in structural supportive excavation. All right, so this goes back to the 40s. The first SB walls were experimental. The idea was if we can drill a boring with bentonite water slurry mud for an oil well or a test boring, why can't we make a continuous trench? So the first walls that are documented are SB style walls in California in the mid 40s. In the late 40s, the Italians built one using a cementitious slurry, a self-hardening slurry. And in the early 60s, they were both used in Europe. But by the mid 70s, most of Europe had went with self-hardening slurries, and most of the US went with SB. And that's a topic of another conversation, how technologies can diverge over time. As I mentioned earlier, the quantum leap in the use of cutoff walls was the 1980 passage of CERCLA. And since the 80s, there's huge developments in the slurry itself, biopolymer slurries, biodegradable slurries, in situ mixing, they've all increased. So our portfolio of ways to build a cutoff wall has dramatically increased. So here's the construction. Schematic, you excavate under a head of bentonite water slurry. The sole purpose of the slurry is to maintain trench stability. And then you replace that slurry with something. In the case of our soil-bentonite cutoff wall, we replace it with a mixture of soils and bentonite to create a high slump material that goes into the trench. And once you get this little schematic going, you just sort of move along and you backfill at the same rate you excavate. And whether you use excavated soils or whether you import soils will depend upon the quality of the excavated soils. But that's the schematic. You can see pictures here on the left. A backhoe with a long stick on it is coming up along a vertical face with a bucket load of soil that is excavated from within the trench. It's going to take a moment to drain off the excess slurry, and then it's going to swing across and put that excavated soil in a pile. And if that has the suitable average grain size distribution, that'll be blended together and put back in the trench as the backfill. So again, the slurry wall name comes from the means of trench stability. The Soil-Bentonite name comes from the backfill. And you can see on the right here, just a fish tank with some sand in it. So for every meter of excavation, if you didn't do something, you'd have about a 4 meter wide trench. Whereas when you excavate with bentonite water slurry, there's really no limit. The equations basically depth drops out of the earth balance equations, and you can dig as deep as you want. Really, our limitation is equipment based, not technology based, and so you can see the stabilized sand by excavating with bentonite water slurry. The second stage of this technique is the backfilling. And in this case, this was an imported backfill. The excavated materials were unsuitable, so we imported a backfill, put it along the side of the trench, added slurry to it from the trench, blended it together into this homogeneous blend of soil, bentonite, and water. And you can see it flows into the trench. It's like a thick viscous liquid. In fact, you can analyze it as a thick viscous liquid. And depending on your permeability requirement and the grain size of the soil, that may be all you need. Sometimes you may want to add additional dry bentonite if the soils don't produce a low enough permeability for your project. So move into some of the things we've learned here. This is an excavation one. So this drawing is what I saw when I was a graduate student at Purdue, and this was published for years. Backfill sloughs forward, backfill placed here, like there's this surface that's just going to move horizontally as you backfill and as you excavate. And this was, I picked the latest one I could find, June 85. And no disrespect to Chris Ryan meant, but it was in one of his papers. But here's a paper by November 85, where we did studies, numerical studies and lab studies, both as from a soil mechanics standpoint and from a fluid mechanics standpoint of a thick viscous liquid. And what really happens is you place some backfill here, it causes a little mini failure, and this stuff just flows down just like a viscous, thick viscous liquid on top of the other previously placed backfill, which then gives rise to really making sure we understand that there's nothing on this slope, so we don't entrap unsuitable materials if you could even consider these as lifts, as we place one lift upon another lift upon another lift. So that was helpful in improving the quality control of the material. We also knew by just observing the trench that there would be settlement. And this is some settlement plates that monitored a 7 meter deep soil bentonite trench, the one that was shown in the backfill placement picture. And you can see, a couple 100 millimeters. And you can also see, for those of you who are civil engineers who remember your soil mechanics class, it takes the typical Casa Grande consolidation curve. You've got primary consolidation and you have secondary, and the primary is finished somewhere around a month or so, but the secondary goes on forever. This data goes out, I don't know, 3,000 or 4,000 days. I think it's 7 or 8 years of data. So it consolidates, and we have to be aware of what is the impact of that consolidation on your project, what is the impact of that consolidation on the properties, which I will get to in a moment here. But it not only consolidates vertically, but it consolidates transversely, that is perpendicular to the axis of the trench. This is inclinometer data showing the transverse movement. And first of all, the movement's much less in the horizontal direction than it is in the vertical direction. It's basically squeezing the material as the soil on both sides of the trench develop stresses that move towards active earth pressure stresses, and the displacement is obviously much less, and that also goes on. This is square root of time, so this also goes on. So this is also about 7 or 8 year data. So you need to be aware that there's going to be movement, lateral movement, which is actually going to cause some vertical movement of the ground. So if you have structures near the trench, you have to be aware of how that's going to influence the settlement of any structures that might be near the trench in the long term. Importantly, in in addition to the settlement impacts, is how does that affect the state of stress? And here's a cartoon that I published in '85 in a Has Waste conference in DC. And I recognized early on that when you place this backfill and it settles, there's going to be load transfer along the side of the surface. That load transfer is going to reduce the stresses in the wall. I had no idea what they were, but this is the theoretical total stress, the geostatic, if you will, just the weight of all the material above a given point. And I conjectured that the actual stresses are going to be something less. Didn't know how much, took a while to get to that solution. But here's some data from '95 from a project near Bucknell, where we were able to do vane shear and consolidation testing. The client let us hydraulically fracture the wall. And the two most important lines are the geostatic calculation in purple and the analytical solution of basically a closed form, so-called arching solution, actually, that was taken from Terzaghis calculation on how to calculate the forces on a pipe in a narrow trench. And you can see a huge difference as you go deeper. And well into the '90s, 2000s, I would ask at a conference, who uses geostatic to calculate the state of stress in the trench? And most of the hands would go up. And we'll see that causes a big error and there are other solutions, there's so-called there are solutions that account for the lateral earth pressures as well, but these are sort of the two extreme solutions for stress. And the reality is the stresses are closer to the red line, way closer than they are to the purple line. So here are some actual measurements of stress in that same wall after about 8 years. And you can see the geostatic is calculated. These are total stresses. And then here are the transverse, the longitudinal, and the vertical stresses. In general, the vertical stresses should be the lowest, but there's not a big difference in these values. We're using earth pressure cells, but generally you can see the transverse is the highest because the side walls are squeezing in and there's a rotation of major principal stresses. If we move to effective stresses, however, which are what control the behavior of soils, meaning the total stress minus the pore water pressure, and the pore water is down about 2 meters here, there is a huge difference between the computed effective stress and the actual measured effective stresses. And number one, and number two, they're very low. We're talking 10, 15 kilopascal stresses down at almost 7 meters. And thirdly, they're almost vertical, which goes back to that original closed form solution, the closed formed arching solution. So why does that matter? Well, it matters most importantly because the hydraulic conductivity can be very stress dependent. Shown on the left here is a plot of hydraulic conductivity, and these are triplicates, so it's an average, as against the log of the effective stress. And this is a cutoff wall for a levee in Birdsboro, Pennsylvania. And you can see that as the effective stress was increased from something about 8 to close to 200 kilopascals, we have a 1, 2, slightly over 2 order of magnitude decrease in permeability. and we kind of knew this not so quantitatively, but back when I was full-time in consulting, when I would assign a lab test for permeability, the lab supervisor would joke, "What number do you want it to be?" Because they could simply vary the effective stress to produce pretty much any number needed. Um, but if you want the most accurate number, you need to be using the effective stresses that exist in the field, which are these low values. The second thing you'll see on this plot are error bars. And you can see that by the time you get to high stresses, the replicates pretty much produce the exact same number. But as you have less stress on the sample, little anomalies, a little pocket of slurry, a little pocket of less well-mixed backfill can have a big impact on the hydraulic conductivity. So not only does the permeability is it reduced at lower stresses, but the variability is increased at lower stresses. Now, this is a case study. This is one particular soil. So to systematically investigate this, one of my students, who's now a professor in New York, looked at different soils with different bentonite contents, and I picked the other extreme, opposite of Birdsboro, and this is a very low fines content soil, entirely granular, so a lot of grain to grain contact. And you can see that instead of 2 orders of magnitude permeability, there's almost no change. In fact, it seems like it got higher with stress. That's probably just some averaging here, but it was only at the highest bentonite contents that you saw maybe a half an order of magnitude drop. And these are from 0 dry bentonite to 5% dry bentonite. So while we know there's an impact of stress on hydraulic conductivity, the magnitude of that impact is highly dependent upon the grain size distribution of the soil used to make the backfill. And we'll speak to that more in later in the talk as well. The other thing that it influences is the bentonite content. Sometimes we don't use any dry bentonite. Sometimes we have to add dry bentonite. And the more dry bentonite you add, the more stress dependent the hydraulic conductivity is going to be. So now that we think we have a handle on hydraulic conductivity and stresses, how does it perform in the field? So this is a picture of the power plant nearby that the first slide of stress came from, where I showed the closed form solution and all the in situ testing. And this is a coal ash waste pond. It was leaking like a sieve. Their first effort was to throw stone on it. And their second effort was, this was PP&L. They had never had a slurry wall before, and power companies are like doing things they've always done before, but they were convinced to put a cutoff wall through here. And as soon as they did, this dried right up. So they did the worst part first, and then it worked so well, they decided to do the rest of the pond more for environmental than for dike stability cases. And in fact, so they built one section in 81 and one section in 87. Well, we went in somewhere around 88, I think 89, somewhere in that period of time. And we did some in situ testing, and we found the wall that had been in for a long time. Because this is an operating plant, this water level was constant. There was no fluctuation. It wasn't a river. It wasn't groundwater going up and down. This had a controlled outlet. So part of this wall was permanently above the water table. We found when we took and resaturated the samples, took Shelby tubes, the permeability had dramatically increased. In other words, the material had dried out and desiccated, whereas below the water table, it was fine. The newer wall was beginning to desiccate, but we didn't have nearly as much impact. So again, that led to, if we're seeing that in the field, how can we look at this systematically? So this is a paper, sorry, there's no reference on it, from the Canadian Geotechnical Journal, where we looked at cyclic wetting and drying of some samples at different suction pressures, and we also did different bentonite contents. So this is just one slide from that paper. And instead of plotting K directly, we plotted the ratio of K. In other words, did it go up, increase 10 times, 100 times, 1,000 times? Um, and so what you can see on this slide are the cycle numbers. And the first one in black is zero suction pressure. In other words, we took the sample out of the mold, we put it in the mold, we did the same sample handling as the rest of them. We just didn't apply a suction pressure. We wanted to make sure our procedure didn't alter the hydraulic conductivity. So you can see that line straight. But now when you start talking about 50 kilopascals, 400 kilopascals, 700 kilopascals suction pressure, these higher suction pressures, it only takes about 2 cycles of wetting and drying before you got a 100-fold increase in hydraulic conductivity. And then we're up to 10,000-fold increase in hydraulic conductivity by the time we get to 5 cycles. The lower suction pressures, it doesn't get as bad, and it seems like maybe it's going to bounce around some smaller increase. But you really need to be aware if you're using soil bentonite in an arid environment. I remember I got called out and drove north of Phoenix, and it was like desert, and they wanted to put a 100-foot deep slurry wall in the desert. And the water table was like 110 feet down. And it was a short consulting job because I said it was a bad idea. So the takeaway message is they need to be covered. You need to prevent desiccation, and because desiccation can result in hydraulic conductivity increases. And that's particularly true if you got a levee where it's by definition wetting and drying. So the other thing that can happen to a wall in environmental applications is what we call compatibility or incompatibility. Um, you put the wall in, it's made with potable water, but the chemistry of the bentonite and its swelling, the swelling is reversible. And if the swelling is reversible, the bentonite's not as effective in plugging the voids. So what you see side by side here are 2 plots. One is aniline at its solubility limit, about 30,000 parts per million. That's an organic base with a low dielectric constant. There's a little bit of consolidation that goes on when you first set it up in a triaxial cell, but then you can see that, the aniline really bounced around. This is 2.5 pore volumes. Really no effect if it's a dissolved constituent. And that's generally what we find to be the case when we do site-specific landfill leachates and the like. On the other hand, if you have a NAPL, here's testing with water, and then we put the pure NAPL into the sample. And this went up, 1, 2, 3 orders of magnitude. Basically, the low dielectric of the aniline caused the bentonite to shrink. And this was a pretty open format base soil. It was a sandy base soil. So the permeability went way up. It did begin to level off, and that's because the perms will level off at the permeability of the base soil. Um, but if you have organics, generally you'll run a site-specific compatibility test, but generally you won't expect incompatibility if they're solubilized. But if they're NAPL, then you really have to pay attention to how widespread it is. Is it really floating product or sinking product everywhere? And the magnitude will depend upon the base soil. Inorganics are actually seemingly a little more complicated. You don't have to worry about these at this point in time, but we try to use relatively clean, if you will, mixing water. But what the inorganics will depend upon, the rate of change will be concentration dependent. The magnitude of the impact will depend upon the ion valence. So the sodium bentonite is the principal ion, is cation is sodium +1. If you permeate it with calcium chloride or any sort of calcium rich fluid, you're going to exchange the calcium on the bentonite for the sodium, and the bentonite will shrink and the permeabilities will go up. And so the answer to that is sort of understood, but in terms of colloidal chemistry expectations and the Goy-Chapman model, if you will. But the answer is you need to run site-specific compatibility tests. Now, if you build a wall that is totally impermeable, um, i.e. 10 to the minus seventh or less, once you get below 10 to the minus seventh, the the contaminant transport through the wall is no longer controlled by advection. It's controlled by diffusion. So number one, getting much lower than 10 to the minus seventh doesn't do much for you because it's already a diffusion controlled wall. And if you really have strict criteria where diffusion through the wall is an issue, a lot of work has been done in measuring diffusion coefficients. Here's just one plot of some of the data. Um, Kristen Sample-Lord at Villanova put this plot together. Um, Basically, diffusion coefficients are relatively insensitive to the backfill, where so far I've said almost everything is sensitive to the backfill composition, and compatibility sensitive to the valence of the cation and the concentration. But diffusion tends to like be in a world of its own. And so if you know the free solution diffusion coefficient of your constituent, you can pretty closely estimate the diffusion coefficient for use in your advection diffusion equation, as somewhere between a tenth and half of the free solution diffusion coefficient. So that actually makes what would otherwise seem to be a complex topic a little simpler. Admittedly, on a lot of projects, we don't worry about diffusion. Sometimes we do. Um, but we do now have information that if we want to deal with it, we can deal with it. So the last of our new, if you will, topics is this membrane behavior, also known as ion exclusion. This is a sample of a picture of test equipment we had at Bucknell, where basically you circulate two different concentrations at the porous stone top and bottom, and the samples in the center. And these are flow pumps. So it's a constant volume circulation. And that gradient difference where there's no flow across the sample, it creates a pore water pressure. Uh, if if we had flow, it would respond to a pore water pressure. So we define chemical osmotic efficiency as basically it's defined in terms of the pore water pressure buildup. And the values range from zero. In other words, if this were a clean sand, the solutes would be free to diffuse, um, and we'd soon have equal concentrations top and bottom. And one is an ideal membrane. That means you can circulate this forever at two different concentrations, and those concentrations will remain the same. There'll be no diffusion from one up to the other. So between 0 and 1. So we tested both lab-made samples and field samples, but SB samples exhibit some membrane behavior. Okay, and you can see the pore water pressure buildup. These are and that pore water pressure buildup is translated into a chemical osmotic pressure, which is then used to compute these efficiency coefficients. But they're generally low, certainly all less than 20%. So for the most part, again, you can disregard osmotic behavior, but osmotic behavior can help the transport, because osmotic behavior sometimes can be in the opposite direction, osmotic flow in the opposite direction of the hydraulic gradient. So in other words, it can subtract from your hydraulic gradient or subtract from your diffusive gradient. For now, I would say the standard of practice does not take advantage of that. Who's to say what will happen as time progresses? So how does all this new understanding of how walls behave translate into our design? I think it's well captured on this slide. If you look at this cartoon here with progressively smaller particles, let's call this fine gravel, coarse sand, medium sand, fine sand, silt, low plasticity clays like kaolinite, silts in here. And then finally, you put 1% bentonite by weight. The bentonite's going to certainly drop the hydraulic conductivity, but you're going to have an inert matrix that is, first of all, inherently has a low permeability, think glacial till. And secondly, it's going to have a low compressibility because the grain-to-grain contact, which helps us on the stress side. So for the optimum design, we want to use a well-graded backfill to make a well-graded soil to make the backfill. We want a reasonably high natural fines content, 20 to 50%. If it gets too high, then you lose this grain-to-grain contact, becomes more compressible, it becomes more stress dependent. We really want to use a low bentonite content because the bentonite is the one that's reversible. And because the low bentonite content is reversible, that's the one that's most likely to be incompatible if you have a high bentonite content. So the result is low permeability, low compressibility, and your best or optimum compatibility. And so you can translate this cartoon into a grain size distribution chart, percent finer than by weight. And I probably should have labeled this as, um, clay, silt, sand, gravel. But you really want a nice, well-graded material in your design. If you don't have it at your site, you can supplement your site. You can bring in more fines, or you can, if you've got open sand and gravel, or you can bring in some sand and gravel if you have too high of a clay content. Sometimes, often, that's cheaper than just pumping more bentonite into the mix, cheaper and better. So that's how it transfers. So to sort of put a design summary on this, we know now that the SB hydraulic conductivity is highly stress dependent, depending upon the grain size distribution, and the dependent stress increases with increasing fines content. We know that mixing bentonite water slurry with base soils, we can do this as a calculation to get the necessary slump flowability that you saw in one of the early slides. That basically automatically adds about 1% bentonite to the mixture, 1% by dry weight. So you cannot help but get some bentonite in your mixture just in getting the material to be a flowable, thick, viscous liquid. The hydraulic conductivity, often our target of 10 to the minus 7th, can readily be achieved without additional dry bentonite for many base soils. Not all of them, but many of them. We can reduce the hydraulic conductivity either to this value if it's too high, or even lower by adding additional dry bentonite to the mix. And that's done by spreading it around where that bulldozer is making the backfill. And it's typically an additional 1 to 3% additional dry bentonite. If we want to reduce the risk of incompatibility on an environmental site, we want to use the least amount of bentonite since the bentonite swelling is highly reversible. So if we put these things in sort of a bulleted list, and then I'll talk another bulleted list in a minute, but what I presented here, we now understand, these are things we didn't understand when I was a student at Purdue. We understand backfill movement beneath the slurry. We now understand much more about the state of stress, and we can compute that, and we can use that in our laboratory testing because we know we understand the influence of effective stress on hydraulic conductivity. And we know the consolidation of the backfill affects the state of stress, and the state of stress affects the hydraulic conductivity. We have good knowledge about hydraulic conductivity of SB mixtures. We have built millions of square feet of SB cutoff walls in the last 50 years. We have run tens of thousands of hydraulic conductivity tests on SB mixtures. So we have a good handle. Contractor can pretty much look at a profile and know whether he's going to have trouble making the product or not. We are now beginning to understand durability can be an issue at some sites, particularly in wet-dry cycles, or I didn't talk about freeze-thaw cycles, but we certainly need to protect against those. We now understand diffusion, although we don't actually move this much into design. Occasionally we do. I can think of one project recently where we were concerned with diffusion. Osmotic behavior, I've yet to see be incorporated in design because it usually actually adds to our safety factor. And a lot of work has been done compatibility. Again, thousands, if not tens of thousands of compatibility tests have been run for cutoff walls around for environmental containment. Um, at a higher level than these sort of details about what we know, we do know that we've been using these successfully since the early 80s. So we have a pretty long track record of post-closure monitoring to say these, if properly designed and installed back in the day, these walls hold up. After all, they are geologic materials. They're not going to go anywhere. Um, Experience by contractors, experience with designers for um, is now widely available. At the time, there were only a handful of contractors. There were only a handful of people who had ever even done a wall. Um, we used to joke if you had read about a project, you were knowledgeable. If you had done it once, let's see, once you were anyway, if you'd done it twice, you were the expert. Um, that, but that's not the case anymore. There are a lot of people with a lot of experience in both design and construction, which is all helpful. The means and methods, contractors have been quite innovative. And so that's increased the range of materials that we can use, the depths to which we can cut these vertical barriers and slurry walls. And so we can do these much more effectively to much greater depths than we could when we started this process. Our developments and understanding of stresses and compatibility have improved our ability to design these for environmental containment. And, this is sort of a more opinion piece on the last one, but I know a lot of times we want to get the last molecule out of the environment and we want to get that molecule out regardless of what cost, but we really don't have enough capital in the world to get every molecule that we put into the environment out again of contamination. And if we just are looking for long-term protection of the public health and the environment, SB cutoff walls are an extremely sustainable method to do that. And if you think of, you know, carbon emissions and the bigger sustainability evaluation between remedial measures, you'll find that soil-bentonite cutoff walls often achieve the most sustainable. Let me see how I did that. There we go. They achieve the protection of public health and environment in a very sustainable manner. So with that, I'll say thank you for your attention, and I will take any questions.
Thank you. Thank you very much, Jeff. That was a great presentation. If anyone has any questions, you can either raise your hand and ask it live, or you can enter it into the Q&A at any time. Okay, so let's see. We've got first question from Matt DeGracia. How does the addition of GGBFS affect the wet-dry cycling sensitivity for systems with deep groundwater?
That's a good question. So granulated ground glass furnace slag is used not in conventional SB walls, but they're used in self-hardening slurry, and they're also used in situ mixing, where you would have cement and Portland cement and slag. The durability is greatly increased. I had the opportunity to participate in the excavation of a very old slurry wall in England around a coal tar site and permanently above the water table, although of course it is damp there, so it wasn't exactly an arid environment, but they're much more durable if they're kept moist. Now, if they dry out, if you've ever taken a sample and put it on your desk and let it go completely dry, they turn to powder because a self-hardening slurry is only about 25% solids, where these are about 85% solids. But they definitely, if slag is an ingredient, it adds to durability.
Okay, we have another question that came in from Juliet Torres. Can ambient temperature preclude slurry wall installation, for example, in Alaska?
Yes, I mean, you, generally there's a criteria, I don't know, like 30 degrees or something that if you have surface temperatures that are very cold, your mixing water is going to freeze. The bentonite slurry will freeze at a slightly colder temperature, but you have to deal with the mixing water. So we tend not to build them when the average daily temperature is below freezing. A little dip doesn't matter, and overnight doesn't matter too much. But during the working day, you pretty much need to be working in temperatures above freezing.
We have a question from Carl Harms at the Army Corps. Are there sites where segments of soil bentonite walls have had to be repaired or replaced due to poor performance?
Well, yes. Uh, in terms of, in my experience, it's all been during construction. So there was a Superfund site in, Ohio I worked on where it was a perimeter circumferential cutoff wall for along the Ohio River. And two things happened. The contractor didn't go deep enough. And so an early portion of the wall had to be completely taken out again and redug to the proper depth. And then they were using a long stick backhoe and they were allowing the backfill slope to push forward under the stick. The stick that I showed in the slide was able to come up vertically. If you have a stick that can dig 100 feet, it has to reach out, and then material falls off the backhoe. So poor QC there, they let, and so when after the wall was built, they went back and they found all these inclusions of soil that had dropped off the backhoe into the wall. So they had to essentially go in with augers and remix the wall. They didn't have to redig it or anything, but they did have to remix the wall for these inclusions. And a similar project in, I want to say Wisconsin or Minnesota, although there it was just excessive sedimentation. And sediments often will have a very low permeability in and out of themselves. But if you allow excessive sedimentation, if remember the one of the early slides, how the backfill moves down the slope, and you trap that sediment in the wall, then you have a window, if you will, of slightly higher permeability. But as far as walls that have been in and operating, and then 5 years later, somebody says, oh, there's something wrong with this wall, I've not seen it. I've heard rumors that some of the cutoff walls built in the Sacramento district that are basically permanently above the water table in that environment have shown signs of degradation over time. But I've not seen that in the published literature. I've only heard that anecdotally from people.
Okay, the next question is from Kyle Metz. In oil and gas drilling, they'll pump LCM if a permeable zone is encountered and mud losses occur. Is there a similar product required if slurry loss occurs during construction? And how does this affect the performance of the soil bentonite wall?
So slurry loss during construction is a big deal. We need to be aware of it, of the possibility. It can happen around a landfill. That landfill project I showed in Maryland, we had to actually put the wall across a portion of old landfill, and we had slurry loss in the trash. If it's moderate slurry loss, you see in this closure slide here a pond. The guy's actually riding around in his little motorboat in it. A lot of projects, if there's a potential for slurry loss, will manufacture a large volume of slurry that can be pumped to the trench on short notice. And that would handle things like, leakage into trash or into an open space. If you're in limestone where there's a cavern that would take an infinite amount of slurry, then you need to, they often backfill. On one project that Chris Ryan, it was quoted in the one slide when he was a contractor, we discussed this, and he said the main thing you do is throw money at the trench. And what he meant by it is he had a source of ground used money which thickened the slurry. So when they would have slurry loss, they would just throw that ground money in the trench, and that would thicken the slurry enough to stop the leakage on one particular project. So every project's a little different, and it depends on the magnitude of loss. I would say by far the most common way to control slurry loss is to have slurry on reserve, and while simultaneously just dumping any old backfill in the trench, knowing you're going to have to dig it out again later.
So we have a follow-up about the question on repairing these walls. If you suspected that there was an issue with a soil bentonite wall sometime that's well after construction, what ways could you investigate it? Drilling, geophysics, or something else?
I'm not a big fan of geophysics for the cutoff wall itself. This project that we measured all the stresses on, we also had a segment where we did geophysics and we purposely buried defects. We would take a sandbag and bury it in the wall, and then our geophysicists claimed they could go back and find it. Not really. So the easiest way is with drilling. If the defect is small, it may have a small impact, but if the defect is large enough, you would find it with drilling. If you were pumping across the wall is also very difficult, trying to build a cell, trying to measure gradients across the wall. If you're using the wall for dewatering, of course, you're going to excavate on the inside and you're going to know whether you have leakage or not because you're going to have excessive seepage in a given area. Um, but for environmental sites, normally the way they do it on a system-wide basis, not so much on individual. That is, they have monitoring wells, they have baseline contaminant concentrations, and they're looking for those contaminant concentrations to diminish over time. And if they're not diminished over time, the area where they're increasing would be the area where the wall would be suspect.
I've got a question from Hao Zhang. Let's see. For vertical barriers as part of site remediation, when do you think we should select a slurry bentonite barrier wall instead of a permeable reactive barrier wall? And what's the criteria for selection? Can we combine these two types of vertical barriers for certain sites, such as for PFAS?
Yes, I'll start yes with you. You can combine them, and that's generally the funnel and gate approach. That if you want to treat the groundwater and you want to do that with a PRB, you can't really build an entire perimeter PRB or even an entire downstream PRB because of cost. So you'd build a low permeability cutoff wall, which would then funnel the contaminants in the groundwater to your permeable treatment zone. Um, the decision of whether to use containment or treatment is really the high level decision. Are the contaminant concentrations low enough to be left in place if they're migrating into the environment and groundwater isn't becoming more contaminated? Um, so if they're not, if you're going to have treatment, um, then you have various treatment options. Say for PFAS is what you brought up. There are various treatment options, and one of them could be an in situ treatment via funnel and gate. So that would be a combination. But usually that decision of whether containment, and once you get a containment decision, then there's a decision of what's the best type of vertical barrier. Is it a soil bentonite cutoff wall? Is it some other technique? That depends on geology, site conditions, et cetera. But really, the higher level decision is one of, can the contaminants be left in place with some other um, treatment system, or perhaps a little bit of pump and treat, or just hydraulic gradient control, or do people want the concentrations lowered from their current concentrations to something lower before the site can be suitable for a passive containment system?
I think we'll maybe wrap up with one last question that's actually coming in from a couple different people. What are the biggest questions or areas that we still have questions about and should focus our research efforts on moving forward?
I think my biggest concern is how they're performing in sections where they're above the water table. How do they perform in dikes and levees over the long term? Can you use them in a humid environment but not in an arid environment? What is their performance of where in zones where they're above the water table, or more dramatically where there's a fluctuating water table? So even environmental sites that are often actually along rivers, the water table may be down in the summer when the river's low, and it may be up in the spring when the river's high. And, are the walls adequately performing in those areas? And, again, an anecdote, I worked on a Superfund site in California where, to me, it was Southern California, and we should be monitoring the cutoff wall because a substantial part was above the cutoff water table. But when I suggested it in a meeting, the contractor immediately objected because they were worried they would have to fix it. The designer objected because they recommended it, and if they found out it didn't work, that would be bad. And actually, every regulator objected because they sold it to the citizens as a cutoff. And if they went back 5 years later and it wasn't working to the original portion, the regulators would have egg on their face. So there's a big disincentive for long-term monitoring. And if we could overcome that disincentive, we would have a better understanding of how they perform in the zone of the fluctuating water table and the area permanently above the water table.
All right, well, thank you, Jeff. If anyone else has a question that you didn't get to ask today, you can reach out to Jeff directly via his email address here. A link to the form for PHCRA has been posted. There was an issue with that link, so if you need that form, please send an email to daniela.7@parsons.com to be able to get credit. And if you missed any of the questions or content, or just want to refer back to this presentation, there'll be a recording posted on our YouTube channel in the next week or so. Our next webinar will be on January 21st, 2026, the same time, 12:30 to 1:30 p.m. Eastern Time, and there'll be more details posted in the next 2 months about that. Thank you to everyone who joined us for today's webinar, and we hope to see you again in January.